Hello, everybody. It's my pleasure to talk to you today about optimal group testing, which is joint work with Amin, Coja-Oghlan, Oliver Gebhard, and Max Hahn-Klimroth, all from the University of Frankfurt in Germany. Group testing is a prime example of a statistical inference problem where the goal is to discover the ground truth from some observed signal. It thereby fits nicely into a broad range of problems such as compressed sensing, CDMA, sparse PCA, or the stochastic block model. So what is group testing about? Suppose you have a population of n individuals, out of which k are infected by some rare disease, and k scales as n to the theta for some theta in 0, 1. The naive way of finding out who's infected and who's not would be to test every person individually. But we can do better than this. Suppose you have access to a pooled binary testing scheme where you can test groups of individuals, and a test returns positive if and only if there's at least one infected individual included in the test and negative otherwise. The goal of group testing is to infer the status of the individuals, which we typically denote by sigma, with a minimum number of tests m. There are two guiding questions in group testing which also occur for many other statistical inference problems. First, the information theoretic view, which asks for the minimum number of tests, regardless of computational resources, to infer sigma with high probability. And second, the algorithmic view, which asks for the minimum number of tests such that a polynomial time algorithm can infer sigma with high probability. To get started, we typically consider two settings of group testing, adaptive and non-adaptive. In adaptive group testing, we perform testing in several stages, and the test design of a later stage might depend on the results of an earlier stage. To illustrate this principle, let's look at an example from Dorfman in 1943, who was the first to put forward the idea of group testing. He suggested to test a group of individuals in the first stage, and if the test is negative, we are sure that all individuals in this test must be healthy, and we are done. And if the test is positive, we would test all members of this group individually in a second stage. Conversely, for non-adaptive group testing, all tests must be specified up front. This can be best visualized using a random bipartite graph where on the one side, we show the individuals, and on the bottom, we show the tests, and the graph structure encodes which individuals participate in which tests. Now, the goal in non-adaptive group testing is using the test results at the bottom and the graph structure, which is at our disposal, to identify who's infected and who's not. So what was the state of play in group testing research prior to our work? Looking at information theoretic lower bounds, there's a simple counting argument that says that the number of test outcomes, 2 to the m, must exceed the possible configurations n choose k, which by applying Stirling's formula just gives us the universal information theoretic lower bound as 1 minus theta divided by log 2 times k log n, where again k scales as n to the theta. For the random regular bipartite graph, which is a special case of a non-adaptive test design, Johnson, Aldrich, and Scarlett in 2019 and ourselves proved in information theoretic threshold that coincides with the universal information theoretic lower bound for some values of theta, but diverges for larger values of theta. Coming to algorithmic upper bounds, two simple non-adaptive algorithms, COMP and DD, were heavily researched in recent years. And by today, their phase transition is well established. Scarlett in 2019 put forward an optimal adaptive three-stage algorithm that achieved the universal information theoretic lower bound. And over the last 2 decades, there have been various attempts to close the open questions in the phase diagram, starting with Berger and Levenstein in 2002, going over Mesar, Tarzia, and Tolinelli in 2008, all the way to recent years. We can visualize those bounds in a phase diagram, where on the x-axis we show the density parameter theta from k scaling as n to the theta, and in the y-axis we show the number of tests. The universal information theoretic lower bound stipulates that in the red area, no algorithm, adaptive or non-adaptive, can succeed to recover sigma with high probability. Conversely, in the blue area, the simple non-adaptive comp and DD algorithms are known that succeed with high probability. And from the work on the random regular bipartite graph, we found a threshold for the information theoretic lower bound in the non-adaptive setting for the random regular bipartite graph, which is shown as the black line in this diagram. So those results obviously give rise to three major open problems that have enjoyed heavily research attention in recent years. The first one concerns the green area in the phase diagram and asks whether there exists a non-adaptive algorithmic gap, or whether we can find a better non-adaptive algorithm than comp and DD that succeeds all the way down to the information theoretic lower bound for the random regular graph design. The second question is whether there exists an optimal two-stage rather than three-stage algorithm that succeeds all the way down to the information theoretic lower bound, the universal one. And the third question asks whether there might exist better non-adaptive test designs than the random regular bipartite graph that succeed all the way down to the universal information theoretic lower bound, or whether there exists some kind of adaptivity gap between one-stage group testing and two or more stage group testing. And in our current work on optimal group testing, we are able to resolve all those three questions. Coming to the first question, the presumably non-adaptive algorithmic gap, what we put forward in our work is a non-adaptive algorithm we call SPIF that recovers sigma with high probability and succeeds all the way down to the information theoretic lower bound for the random regular bipartite graph. The SPIF algorithm is inspired by the idea of spatial coupling from coding theory that has already found applications for in a few instances of statistical inference problems, with compressed sensing being the most prominent one. How does the spatial coupling idea work? Rather than creating a simple random bipartite graph, we enforce a certain geometric structure on the graph. To be precise, we divide the individuals and the tests into several compartments and arrange those compartments along a ring structure. Now, the crucial point is that each individual does only join tests in its own compartment or nearby compartments. Once we have set up this test design, we start by classifying some of the compartments as so-called seed compartments, for which we perform a few additional tests to be able to recover the infection status of each individual in those seed compartments with high probability. Subsequently, we work our way compartment after compartment to the right, classifying the individuals, always using the knowledge of the previous classified individuals on the left. And once we move through this ring structure in the first round, we show that we are able to identify all but k times n to the minus omega 1 individuals correctly. In subsequent rounds, we iteratively move again through the ring and correct errors and show that within at most log n rounds, we'll be able to recover the sigma with high probability. An important point to stress here is that in those subsequent rounds, we do not perform additional tests. We merely use the test results that we've created non-adaptively and use those to identify where we made a mistake in the first round. One point that I would like to draw your attention to is the information theoretic lower bound shown at the top there, which consists of a maximum of two terms, where the first term is simply the prefactor of the universal information theoretic lower bound. And those two components exactly correspond to the success guarantee of the first round and subsequent rounds. To be precise, the first component of the maximum ensures that in the first round we are succeeding in identify all but k times n to the minus omega 1 individuals correctly, while the second component of the maximum is a local stability argument that ensures that we are able to correct the errors we make in the first round in those subsequent rounds. And this insight that essentially the first round of SPIF succeeds all the way, even using the universal information theoretic lower bound number of tests, allowed us to, in a second step, come up with an optimal two-stage algorithm. We call this algorithm ASPIF and show that this algorithm recovers sigma with high probability all the way down to the universal information theoretic lower bound, thereby improving on the result by Scarlett, who provided a three-stage algorithm. How does ASPIF work? It is essentially an extension of the SPIF algorithm that I've presented on the previous slide, and using a similar procedure as put forward by Scarlett in 2018. To be precise, we perform the first round of the SPIF algorithm using the universal information theoretic lower bound number of tests, and are able to identify all but k times n to the minus omega 1 individuals correctly. In the second stage, we test all tentatively classified infected individuals separately and test all tentatively classified healthy individuals in a new group testing instance using the non-adaptive DD algorithm. Both of these components in the second stage work with a lower order number of tests than the universal information theoretic lower bound, thereby ensuring that those two stages succeed as long as we perform more than the universal information theoretic lower bound number of tests. So those two results, the non-adaptive SPIF algorithm, the optimal two-stage ASPIF algorithm, give rise to the question whether there exist better non-adaptive designs that might succeed all the way down to the universal information theoretic lower bound. And the third result from our work on optimal grouping says that the answer is a clear no. There does not exist a non-adaptive algorithm, efficient or not, that outputs sigma with a non-vanishing probability if we move below the information theoretic lower bound that had been previously only shown for the random regular bipartite graph. How do we go about proving this? The proof consists of two steps. In the first step, we show that if theta is close to 1 and we perform less than the information theoretic lower bound number of tests for the random regular bipartite graph, for any test design, we can easily construct a large number of satisfying configurations that are indistinguishable from the true sigma. And we do this by means of the FKG inequality and the Nishimori property. In the second step, we show that if we cannot solve the group testing problem for theta close to 1, we also cannot solve it for smaller theta. And with those three results in place, the phase diagram simplifies significantly. So to recap what we've done in our work on optimal group testing, we've put forward a non-adaptive algorithm called SPIF that is inspired by the idea of spatial coupling from coding theory to show that in the non-adaptive setting, there's no algorithmic gap. We extend this non-adaptive SPIF algorithm to an adaptive two-stage algorithm called ASPIF that succeeds all the way down to the universal information theoretic lower bound, thereby improving on the best previously known result of a three-stage optimal algorithm. And third, we use the FKG inequality and Nishimori property to show that there exists an adaptivity gap in the sense that for certain values of theta, adaptive test designs are provably better than non-adaptive test designs. And with this summary, I would like to thank you for your attention and welcome any questions. Thank you.